Hey gang, this is Mr. Schmidt with a recap of our November 13th, Friday the 13th lesson concerning our forces and vectors. Fun little video here, especially considering how many times I make a trip to the refrigerator in between classes. Here we see what we're looking at for today. Students will be able to add forces in different directions, okay? And the key to do that is to break up our sine and our cosine for any resultant force, and that thus we're resolving the forces into vertical and horizontal components. Okay, we've done this before, but we're going to keep adding more complexity as we try to get more and more realistic situations. Okay, so one of the examples we looked at earlier is if someone is pulling a wagon. As you pull on the wagon, you're going to have both a horizontal and a vertical component to that handle. Notice as you pull up on the handle, you're going to take some of the pressure off the wheels, and that's also going to reduce the normal force going forward, which then reduces the friction force opposing motion. Okay, so as we do things, if we can break everything down into X and Y components like we had in the example the other day, it makes things a lot easier. Okay, so we're not going to do the same example again, but we need to think back that when we did this, first we made sure to break down all forces into individual X and Y components using SOHCAHTOA. Then we're going to move back and forth between Newton's second law and the friction equation. So we can find the sum of the forces in the y direction equals mass times acceleration in the y. And quite frequently, we're going to pick a coordinate plane so that there is no acceleration in the y. So we're going to turn our coordinate plane in such a way that the object is not moving in the y direction. And so we can set that equal to 0 and find the sum of the forces that way. Okay. Next, depending on what they're asking for, we're either going to do some of the forces in the X, or we can use that Y component and that normal force that we've just found and find our friction force, and then apply it back to Newton's second law and the sum of the forces in the X. Okay, so this is important to think about as we go through the examples we'll see later. Okay. Next up was ranking the perpendicular component from greatest to least. Okay, so when we look at this, we can look at the extreme examples and see what we're working on here. Okay, so what we see is that if it was perfectly horizontal, this force normal would be equal and opposite to the force of gravity. Okay. If it was perfectly vertical, it would fall off the wall and have 0 normal force, okay? Assuming there's no other forces applied to the object here, which is something we're going to be changing here very soon, okay? But in this scenario, if the only force is gravity, then there'd be 0 normal force here, 100% of the normal force would be there. So if we were to rank the perpendicular component of all of these, notice they don't say vertical, it said perpendicular, perpendicular to the surface. That's what we're concerned with because that is the normal force and that will eventually affect the friction force. Okay, when we look at those, we see that this is closest to horizontal, so it does go straight in order. This has the greatest perpendicular, this has the least perpendicular force, which is why this would slide the fastest and this would slide the slowest, and so on. Okay, all right, so let's come back to our notes here and look at what does that look like on the diagram. Is if we take that downward force and we break it into the parallel and the perpendicular, we can now see that the perpendicular force is going to be dependent on this angle. Okay, so the greater this angle is, we get more of the purple, more of the parallel and less of the blue, less of the perpendicular. Okay, well, what happens if it's not just one force? What happens if we have lots of forces? So this could be a beam trying to hold up all the pieces of our bridge, or this could be an electron being pulled on by a bunch of different surrounding atoms, or it could be a person with all their friends pushing and pulling on them. It could be any point experiencing multiple different forces. If we want to figure out what is the resultant force on this point, the easiest way to do that is to take one force and then slide the next one so that the tip of the arrow or the head of the arrow goes to the tail of the next arrow. And then we keep adding head to tails for each one of these until we end having used all four of our arrows, all of our forces drawn out, and the gap between where we started to where the tip of that last tail arrow is. That is our resultant. Notice we can start and go in any order we want for our four forces. If we get the magnitude and direction correct for all of the forces we add up, then the magnitude and direction of the resultant will always be the same. Okay, we could also split these up into x's and y's and add up all of our x's and all of our y's, and we would still get the same direction and magnitude as the resultant. So we could do this graphically, drawing the arrows, or we could do this algebraically and trig, finding all of our x's and y's and adding them together. Okay, so this brought us to our example, which was finding the force on the pole. Okay, so if this sign has 50 kilograms of force, then we're going to do 50 times 9.8. It's going to have 490 newtons of force pulling down. Now, if we cut the cable, obviously this whole thing is going to fall down. If we remove the pole, the whole thing is going to slam to the wall. So we know the cable is providing a force, and we know the pole is providing a force. And the question is, how much force is applied to the pole, or how much force is the pole applied back on the sign? Okay, that is what we're trying to figure out. Okay, so if we now look at this, we have the triangle, the 3, 4, 5 triangle, which is, by the way, one of the easiest ways to force something into a 90-degree right triangle. Okay, we can find this angle any combination of the opposite, adjacent, and hypotenuse to find this angle. We could also just kind of skip knowing what this angle is and just know that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay, so this is a clear repetition of SOHCAHTOA. Okay, so if you want to, you could plug this number back in and you'd get the same results. Okay, but we're just going to keep this off to the side, knowing this is our triangle, which means the force diagram is going to be proportional to that. It's going to be a similar triangle. Okay, so first thing we know is we have a 50 kilogram sign. So we can find out how much the sign is pulling down on this point. This point also has string pulling up and a pole pushing out. Okay, thinking back to the example we had, we want to break this up into X and Y components. And if we do that, we can then start following our path all the way around until we find this force. Okay, let me rewrite this. All right, so we had our triangle, and it looks something like this. Okay, it came this way, but what I'm most interested in is there is a force here, okay, and there is a force going this way, okay? those were the two directions of forces for this cable. And we knew that the force of gravity right here is that, okay? So now we've broken everything up into our X and Y components. We can go through and find our Newton's second law. Now, this is a sine, okay? And on a bad day, it's Friday the 13th, maybe this would happen. It might have acceleration, but on a normal day, this should be 0, okay? So that means that our force of gravity plus our force in the y direction have to add up to 0, okay? So this is 490 down. This one is going to be 490 going up. Okay, so that sets up the beginning of our triangle. Now, remember, this was a triangle, though. Okay, so this was our triangle, and this was the same angle we had before, 36.87 degrees. Okay, now we can do this any number of ways we want to find our f of x. Okay, because I know this, okay, we can do opposite and adjacent, okay? Opposite over adjacent equals tangent of theta, okay? Now, if you remember, I wrote down the tangent of theta is 3/4, okay? So now we can plug in these numbers, okay? Remember, we're solving for f of x, so I could also do okay, so I just rearranged that to give me this. Okay, we said that was 490 newtons. We said the tangent of theta is 3/4. Okay, 3/4 times, actually 490 divided by 3/4 should give us 653 newtons. Okay. Just for practice sake, what would happen if we just wanted to know this one? Okay. Well, F1 over Fy. So, or excuse me, opposite over hypotenuse equals sine of theta, right? So we could also do F1 times the sine of theta, okay, equals f of y, or what we're trying to solve for. We're trying to solve for F1. F1 equals Fy over sine of theta. So we could still do 490 newtons, okay? And then we have sine of theta, we already knew was 3/5, okay? And then we could plug that in again, and we could find F1 equals 816 newtons, okay? By the way, someone also pointed out we could have done Fy squared plus Fx squared equals F1, right? Okay, trig gives us lots of different ways to approach a problem and always getting the same number, okay? So you can figure out which is the best way to work for you as long as at the end we have all of the numbers accounted for, okay? So this was 816. All right, so now we know the force in the x, we know the force in the y, we even know the diagonal force, we need that. Remember, our final question here is the force of the pole, okay, F2, right? We wanted to find this force, okay? Well, this force does not have any y components, okay? So we just have to do the sum of the forces in the x. Okay, again, that equals 0 equals f of x plus f2. You know, you could say f2 of x if you want to, but this one only has an x component, so it doesn't matter. So again, these two are going to have to be equal and opposite. Okay, so this cable was pulling in that direction, and the pole is going to be pushing out in this direction. So F2 is going to equal 653 newtons to the right. Okay? All right, so that is our final answer. All right, so if we come back to our notes, I want to point out a few things you can see in this question, which is not going to be true all year. Okay, this is placed at the very end of the pole, exact same place as the cable. Okay, that means we don't have to worry about torque. Okay, torque is going to come up later, where if you have a force at one point and a different force at a different point, and someplace where it turns or pivots, then we have to take all sorts of other factors into play, number one being torque. Okay, we would also have to think about that if this pole had mass as well. The mass of the pole itself would pull down on this cable, which would force more tension on the cable and more pressure against the pole. Okay, and then if you really wanted to be exotic in building this, you could have done this without any bolts over here and just allowed the tension and the compression to apply force to this point. And as the pole was forced into the wall, then friction would keep it in place. The interesting thing about this example is our normal force would be coming out of the wall, and our friction force would be going vertically up the wall. Okay, so your normal force can be in every direction, including perfectly horizontal. Okay, we just have to keep track of all the forces as we go through these things. Okay, so again, as we go through these, we have to keep sure that the forces are broken up into our x and y, into our perpendicular and our parallel. And if it becomes complicated to keep track of your parallel and perpendicular drawing it this way, as long as you keep that angle correct, you can just turn your paper and call this your x and this your y, and you just have gravity moving at some given angle. Okay, and then finally we had the forces acting on a bridge. Okay, so if we have a single point on a bridge, looks like we're looking at one of these points right here, okay, then we're going to have a lot of different forces stacked up to carry the load. Okay, and we're at load 5, looks like it's going to have another component over here as well. Okay, so what we're going to see is that some of the load is going to be distributed on the different beams, and some beams are going to be pulling, some beams might actually be pushing. Okay, there's going to be a whole combination of tension and compression going on here that we'd have to go through the same process, break up our x's and y's, find out our known. Normally the load is the first thing we establish, what the downward force is, and then we distribute it according to algebra to each of the different members of the bridge. Okay, physics, we're going to focus down here. Okay, as you go into engineering, or if you choose to go into engineering, then you're going to have to figure out how does that interact with all of the other pieces. Okay, again, the physics has already been established down here, and then we just have to keep applying the same physics point to point to point to point all the way across. And that's normally when you get a spreadsheet or a computer program to do the algebra for you. Okay. All right, so that finishes up the notes. I do want to point out a couple of things with our forces here, or with our assignment. Number one, it says to use a protractor. So either you can print this or you can try to do on-screen measurements. Notice it says this counterclockwise notation. Counterclockwise notation is kind of like your unit circle. It starts with 0 here, and then we go counterclockwise, okay? It's not always done in all physics, but it is a nice way to be nice and consistent when I'm doing assignments to see if you're practicing. And then the other thing I wanted to mention is, remember when they're doing resolving forces and adding them together, you have to go heads to tails. So the one that's not a resultant force, that's the ending force, must be one of these 2 points pointing together, okay? So these two cannot be added together because they're nose to nose here, okay? So that's how we're going to figure out how to establish them. This looks like it's going to be C plus B equals A, okay? A and B are both going to the right, so there's no way they would add up to equal C, okay? So hopefully this assignment is fairly straightforward, lots of quick questions here, and then you end up with a couple of writing the magnitude of components, getting your triangle set for this one, okay? So with that, you should have a nice straightforward assignment, and hopefully you go into the weekend nice and relaxed, and I wish you all a good day.